Welcome to the deep dive. Today, we're taking on something huge. This image we all have of the Sahara Desert, endless, static, unchanging sand. We're diving into data like from the deep sea, ancient monuments, lake beds, all to show you it's completely different.
It really is. That image,
Yeah.
totally wrong. The Sahara, it isn't timeless at all. It's incredibly dynamic. It cycles. And the core concept we're looking at is the green Sahara, or the African Humid Period. And we're not talking just a little bit greener. I mean, a full-on transformation. Huge lakes, rivers, ecosystems buzzing with life, capable of supporting, well, a lot of people.
Right. So our mission here is to kind of weave all this evidence together. We've got deep sea cores from the Red Sea, the Atlantic. Then there's the evidence from dried up megalakes, plus thousands of archaeological sites. We want to pin down the timing, the causes, what drove these massive shifts. And critically, what happened at the end? Was it purely climate, or did humans maybe play a role in the collapse, especially with pastoralism coming in?
Exactly that. And our sources, they're pretty amazing. We've got these high-resolution climate records from marine mud, dust trapped in ancient soils offshore, and we combine that with big-picture demographic reconstructions using tons of radiocarbon dates from human sites. So the theme really is this complex dance between predictable climate cycles from space, surprising ecological feedbacks on the ground, and how human population density kind of throws a wrench in the works, acting as this major environmental factor.
Okay, so let's start way back. Before the last Green Sahara, just how old is the desert itself? I heard this is actually quite debated.
Oh, absolutely. It's been really controversial. You see estimates from just a few thousand years, all the way back to the Miocene, millions of years ago.
So where does the latest evidence point?
Well, the newer geological work gives us a much firmer anchor. And interestingly, the proof isn't in the Sahara itself, but hundreds of miles away, on islands. We're talking about paleosols, fossil soils found on the Canary Islands, specifically places like Fuerteventura, Gran Canaria.
Okay, hang on. Fossil soils on islands. Tell us of a continent. How does that work?
It works because of wind. Long-range transport, LRT. The Sahara is, bar none, the biggest source of mineral dust on the planet. Those huge dust plumes you see on satellite images blowing across the Atlantic, that dust reaches the Caribbean, even fertilizes the Amazon. Well, that process is ancient.
Right. So what do these specific Canary Island soils show?
They show that North Africa was arid and kicking up dust much, much earlier than some thought. These paleosols go back intermittently into the Pliocene, starting around 4.8 million years ago. And the key thing is the minerals in those soils. They contain lots of quartz and mica.
Okay.
Now, quartz and mica are super common in African continental rocks, but they're really in the volcanic basalt that makes up the Canaries.
So they had to have blown over from Africa. There's no other source.
Exactly. It's a clear fingerprint. So we have solid evidence of African dust hitting the Canaries almost 5 million years ago. The Sahara, as an arid dust-producing region, has been around cycling for a very long time.
Wow. Okay, so it's ancient and it cycles. What's driving these huge swings between desert and, green?
The main engine is astronomical. It's about subtle, predictable changes in Earth's orbit around the sun, Milankovitch cycles.
Right, I've heard of those. Which specific cycle is the key one for the Sahara?
It's primarily the precession cycle. That's the Earth's wobble, like a spinning top, on about a 23,000-year timescale. This wobble changes when the northern hemisphere has its summer relative to Earth's closest approach to the sun, which we call perihelion.
Okay.
So when northern hemisphere summer happens at perihelion, North Africa gets a significantly stronger dose of solar energy during the summer months.
Just from that wobble, it makes that much difference.
It makes a huge difference to the atmosphere. That extra energy basically supercharges the system. It affects the ITCZ, the Intertropical Convergence Zone.
That's the big rain belt near the equator.
Exactly. The extra summer heating allows the ITCZ and the whole West African monsoon system to push much further north than it does today, deep into what's now the Sahara.
And that's what creates the Green Sahara.
That's the mechanism. And it's not just a one-off Holocene thing. This has happened repeatedly over geological time, driven by that precession cycle.
And these African wet periods, they don't just affect Africa, right? You mentioned global connections.
Oh, absolutely. North Africa's climate state sends ripples across the globe. One classic example is in the Mediterranean Sea. During these African humid periods, you get so much fresh water pouring out of the Nile, which is swollen by the monsoon rains, and also from ancient rivers reactivating in places like Libya,
Okay.
that this fresh water forms a kind of lid on the eastern Mediterranean.
Right.
It's less dense than the salty seawater, so it prevents the deep water from mixing with oxygen from the surface.
So the bottom layers of the sea run out of oxygen.
Precisely. It leads to anoxia, deep sea stagnation, and when marine organisms die and sink, their organic matter doesn't decompose fully. It accumulates on the seafloor as these distinct black organic rich layers called sapropels.
Wow. So the Med literally holds its breath because the Sahara is green.
That's incredible. It's a direct teleconnection. And then there's the dust aspect, when the Sahara is dry.
Right. The LRT dust we talked about.
Yeah. When the desert phases are dominant, that dust blows across the Atlantic. It carries vital nutrients, especially iron, to parts of the ocean that are otherwise nutrient poor. This basically fertilizes marine ecosystems, affecting food chains and even the global carbon cycle. Plus, all that dust in the atmosphere reflects and absorbs sunlight, influencing the planet's overall energy balance and temperature. North Africa is a major climate player.
Okay, so to really track these cycles over long time scales, like 200,000 years, we need those natural archives. You mentioned marine sediments. Let's talk about core K11 from the Red Sea. Why the Red Sea? What makes it so good for this?
The Red Sea's geography is almost perfect for this. It's long, narrow, and flanked by these really arid land masses, Northeast Africa and the Arabian Peninsula. So any dust blowing off the land or any sediment washed in by rivers during wet periods, it funnels pretty directly into this deep basin and settles relatively undisturbed. Core KL11 was taken from about 825 meters deep in the central Red Sea, and it gives us this beautiful continuous record covering the last two full glacial interglacial cycles. It captures all the major humid periods and arid phases in that time.
But when you pull up that core, it's basically just layers of mud, right? How do you tell if a specific layer arrived via wind or via a river?
That's where the physical properties come in, specifically grain size. We look at the terrigenous fraction, the bits that came from land, not marine organisms. And we use statistical techniques like end-member modeling, EM analysis, to sort of mathematically unmix the grain size distributions. We're looking for distinct signatures that represent different transport processes.
Okay, so break down these end members for us. What do they represent?
Right. So during the dry desert phases, the glacial periods or other arid times, we see dominance from the aeolian, the wind-blown end members. There are two main ones. EM1 is the coarser stuff, around 65 micrometers. Think fine sand. That tells you about stronger winds, maybe more intense dust storms needed to lift and carry particles that big. It peaks during the really arid, windy intervals. Then there's EM2. That's finer, maybe 20 to 40 micrometers. This is more like your typical lowest dust, carried higher and further, perhaps by slightly less intense but more persistent winds.
So lots of EM1 and EM2 means a windy, dusty desert.
Got it. What's the signature for the green Sahara periods then?
That's the really exciting one. EM3. This end member has a dominant grain size of just 4.5 micrometers. That's incredibly fine clay and silt. This tiny size is characteristic of material transported in suspension within water fluvial transport. It's the signature of rivers carrying sediment into the Red Sea.
So peaks in EM3, that fine river mud, directly track the intensity of the monsoon. Absolutely. The EM3 maxima are our proxy for the African humid periods, and the K11 core shows these AHPs weren't all created equal. They varied in strength. The strongest one in this 200,000-year record was during the Eemian interglacial. That's about 125,000 years ago. But there were other big ones around 198,000, 108,000, 84,000 years ago. And then the most recent one, the Holocene one, peaking around 6,000 years ago.
And this river sediment, where was it primarily coming from?
The analysis suggests the main source for the fluvial input into the central Red Sea during these wet times was the Tokar Delta. This delta is fed by the Baraka River. Now, today the Baraka River is ephemeral. It only flows for maybe 40, 70 days a year. But its catchment area is huge, 66,000 square kilometers.
Whoa.
So the strong EM3 signal tells us that during the AHPs, this massive catchment was intensely activated. We're talking about a river system that was likely flowing much more consistently, carrying enormous amounts of sediment, almost like a major perennial river today. It shows the scale of the transformation.
Incredible. Okay, besides grain size, you mentioned minerals can act like fingerprints to trace the source areas. What do the clay minerals in K11 tell us?
They add another layer of detail, definitely. The most abundant clay mineral is smectite, and its concentration tracks those wet fluvial periods, the EM3 peaks, really closely. Smectite typically forms under conditions of intense chemical weathering, like you get in humid, well-developed soils. So its abundance confirms the presence of extensive, well-watered landscapes on the African side during the AHPs.
What about minerals from drier source rocks?
We also see elite and chlorite. These are more characteristic of physical weathering, basically, rocks being mechanically broken down. They likely come from the erosion of the granite and metamorphic rocks, the Arabian-Nubian Shield, which surrounds the Red Sea on both sides. Their presence, even mixed in with the fluvial signal, shows that the surrounding highlands were still eroding and contributing sediment to the rivers, even during the wet phases.
But you also mentioned something about dust coming from further away, even when Africa was supposedly green.
Yes, and this is where it gets really interesting and shows the complexity. There's a mineral called palygorskite. It's generally considered a diagnostic mineral for wind-blown dust, often forming in arid or semi-arid conditions. Surprisingly, palygorskite persists right through the K11 record, even during the peak humid periods when African dust should be suppressed.
So dust was still arriving from somewhere?
It seems so. The interpretation is that this represents a persistent secondary dust source, likely from further east, maybe the eastern Arabian Peninsula or Mesopotamia, areas that perhaps remained relatively arid even when the African monsoon was strong.
Wow. Okay, so multiple weather systems interacting.
Exactly. And then there's one more, kaolinite. This clay mineral shows a pattern that's kind of independent of the main monsoon cycles tracked by EM3 and smectite. The thinking is that kaolinite might be coming primarily from areas in northern Egypt, like the Sinai or Wadi systems there, and its transport down the Red Sea is likely controlled more by the persistent year-round winds that blow from the north-northwest along the axis of the Red Sea.
So you've got the powerful summer monsoon bringing rain and river sediment. You've got dust possibly blowing in from the Middle East, and you've got these NW winds bringing material from Egypt all at the same time.
Precisely. It really highlights that the atmospheric circulation was complex and regionally variable. You can't just paint the entire region with one brush. These mineral tracers let us tease apart those different contributing sources and wind systems.
Okay, let's zoom in now to that last major green Sahara phase, the Holocene African Humid Period. This is the one humans really experienced, roughly 12,000 to 5,000 years ago. When did things start getting wet again after the last ice age ended?
Well, the lake records from across North Africa show the onset was pretty dramatic. It actually started quite early, during a warm phase called the Billing-Alarud, maybe around 14,700 years ago, a big pulse moisture then. That got interrupted briefly by a cold, dry snap called the Younger Dryas. But then, around 11,700 years ago, the wet conditions came back really strong and they became much more stable. That's when the real transformation kicked into high gear.
And what did that transformation look like on the ground? It's hard to imagine looking at the Sahara today.
It's almost impossible to overstate the change. Lakes expanded massively. We're talking about megalakes. Think of names like Megachad, Lake Fizan, the Chot's Paleo Lake in the Maghreb, Megachad, for example. Estimates suggest it covered up to 361,000 square kilometers at its peak.
Wait, say that again? 361,000 square kilometers. That's huge! For context, that's roughly the size of modern-day Germany.
Exactly. Or, to put it another way, about 15 times bigger than Lake Chad was even in the 1950s, before its recent shrinkage. It was a vast inland freshwater sea right in the heart of the Sahara.
Unbelievable. And this supported different vegetation.
Absolutely, the landscape changed completely. Instead of sand dunes, you had widespread grassland, shrubland, even some areas of woodland. Plant species that today you only find much further south. In the Sudanian and Guinean zones, they migrated northwards, well into the current desert. Records show them reaching up to maybe 16 degrees north latitude in West Africa.
And this greening wasn't just a passive response to rain, was it? The vegetation itself played an active role.
Critically important point, yes. This vast plant cover created powerful positive feedbacks that likely amplified and sustained the humid conditions. Think about it. You replace bright, reflective sand with darker, moisture-holding vegetation. This drastically lowers the albedo, the amount of sunlight reflected back into space.
So the ground absorbs more heat?
Right. Darker surfaces absorb more solar energy, leading to warmer ground temperatures. Warmer ground heats the air above it more effectively, increasing atmospheric convection, rising air.
And that rising air helps pull in more moisture.
Exactly. Stronger convection reinforces the low-pressure system over North Africa during the summer. This strengthened low acts like a giant vacuum cleaner, pulling in more moist air from the Atlantic and the Gulf of Guinea. This feeds the monsoon, making it stronger and pushing it further north, which grows more vegetation, which lowers albedo further. You see the loop?
Yeah, a self-reinforcing cycle. The greenness helps maintain the greenness.
Precisely. It's a nonlinear response that likely made the Holocene AHP more intense and perhaps more stable than just the orbital changes alone would suggest.
Okay, so the environment was undeniably lush. What about the human side? What archaeological evidence confirms people were living there and thriving?
The archaeology provides really vivid proof. In parts of the Western Sahara, for instance, around places like Tifariti, the landscape is dotted with hundreds of ancient stone monuments. And these aren't just simple shelters. We're talking substantial structures, long rows of piled stones, circles of standing stones, and these really impressive burial mounds called bazinas. Some are like 5 meters tall, made of dry stone.
5 meters high. In what's now barren desert, that implies, well, permanence, organization, a settled population.
Definitely. These monuments, some dating back over 10,000 years, strongly suggest people were living there long term, investing labor, developing complex social rituals, likely centered around burial and ancestry.
And then there's the rock art, right?
Wow.
Those famous Saharan paintings.
Yes. The rock art is maybe the most direct window onto the ecosystem. In places like the Archaeological Park, you find these incredible paintings and engravings. And what do they show? They depict animals that simply cannot survive there today. Of course, there are gazelles and antelopes, but critically, they show large animals like giraffes, elephants, even rhinoceroses.
Wow, animals that need reliable water and vegetation.
Exactly. These aren't desert creatures. They require a Sahelian or even a riverine environment with dependable water sources and enough browse or grass. The art is undeniable proof that, for millennia, the Sahara was a very different, much wetter, and biologically richer place.
Okay, so we've established this green, resource-rich Sahara, perfect stage for human expansion. How well can we actually track how quickly people moved in and how much their populations grew?
We can track it with remarkable precision, actually, using radiocarbon dating. Researchers compiled thousands of 14C dates from archaeological sites across huge regions, the Central Sahara, the Eastern Sahara, the Atlas Mountains. By combining these dates statistically, using a method called summed probability distributions, or SPDs, they can reconstruct a pretty robust curve representing relative population changes over time between about 10,500 and 500 years ago. And the results are, frankly, stunning. What we see is a massive, incredibly rapid population increase kicking off shortly after 11,000 years ago.
How rapid are we talking?
The growth rates calculated are extraordinary for pre-agricultural societies. We're looking at rates around 7.7% per generation. That led to something like a 143% increase in the overall population index in just 300 years.
Wow, 143% in 300 years. That's an explosion. People really flooded into those newly available lands.
They really did. It shows just how productive and attractive that green Sahara environment must have been.
But there's a really interesting wrinkle in the timing, isn't there? This population boom didn't happen immediately when the rains returned.
That's a key finding, yes. There's a noticeable lag. The climate itself, the atmosphere, the rainfall patterns shifted towards wetter conditions significantly earlier, mostly between about 12,500 and 11,500 years ago. Yet, this huge human demographic surge we just talked about, it lags behind that initial climate shift by roughly 1,000 years.
1,000 years. Wait, if the environment was getting wetter, why didn't people just move in straight away?
Well, think about it. Just having rain isn't enough to support a large, stable human population. An entire ecosystem needs time to develop, that 1,000-year lag. It likely represents the time it took for the terrestrial ecosystem to fully recover and mature after the preceding dry phase. You needed soils to develop, grasses and shrubs to establish themselves widely, the large animal herds, those giraffes and elephants in the rock art, to migrate in and build up their numbers, the fish populations in those new megalakes to become abundant.
I see. So humans weren't just waiting for rain. They were waiting for the whole food web, the entire resource base, to become rich and reliable enough to support them long term.
Exactly. The population boom followed the ecosystem's maturation. And the people who first occupied this fully developed green Sahara environment, they had a very distinctive way of life. It's often called the aqualithic culture.
Aqualithic. Makes sense, waterstone. So focused on aquatic resources.
Very much so. Archaeologically, we find sites with typical stone tools, microliths, but also lots of specialized gear related to water. Things like bone harpoon points for fishing, and a characteristic type of pottery decorated with wavy lines or comb impressions. These were primarily hunter-gatherer or fisherfolk, heavily utilizing the abundant resources of the expanded lakes and river systems. Fishing, hunting waterfowl, hunting the large mammals drawn to the water sources, that was their core strategy.
Okay, so a very successful adaptation to that watery landscape. But then things changed again, didn't they? Midway through the AHP, there was another big shift.
Yes, a really significant one. Around 7,000 years ago, we see the widespread adoption of domestic livestock, specifically cattle, and also goats. This is the beginning of pastoralism in the Sahara. And interestingly, this shift coincides with another major population boom in the SPD curve, particularly between about 6,700 and 6,300 years ago. It seems introducing livestock allowed people to exploit new ecological niches, maybe moving away from just the lake shores and rivers into the expanding grasslands. We even have direct evidence, like chemical residues on pottery, from sites like the Caucasus Mountains in Libya, showing they were processing milk around this time.
So pastoralism wasn't just adopted, it fueled further population growth and expansion.
It appears so. It added a new, potentially more mobile and controllable food source to their toolkit.
Now, looking at those population curves, you mentioned they covered vast areas, central, eastern, Atlas Sahara. How similar were the patterns across these huge regions?
That's another striking finding. The demographic curves for these three massive regions, covering over 3 million square miles, show a very strong correlation. The ups and downs, the timing of the booms and busts, they match up remarkably well.
What does that synchronization tell us?
It strongly suggests that the primary factor driving population dynamics across this enormous area was large-scale climate change, the influence of the monsoon system. If the main drivers were more local things like resource depletion in one area or conflicts between groups, you'd expect the population histories in these different regions to look much more varied, more out of sync. But they're not. They move together.
Climate as the main conductor of the orchestra. But was there anywhere that didn't follow this pattern?
Yes, and it's an important exception that proves the rule, in a way. The western littoral region, the Atlantic coast. The demographic reconstruction for that coastal area shows a completely different trajectory. There's no clear correlation with the big boom and bust cycle of the AHP seen in the interior.
Why would the coast be different?
The likely reason is their resource base. Coastal populations probably relied much more heavily on marine resources, fishing, shellfish, marine mammals, and those marine resources are far less sensitive to the fluctuations of the African monsoon that were drastically changing the interior. So their relative stability, while the interior populations linked to the monsoon were undergoing these dramatic swings, really underscores how dependent those interior societies were on that fluctuating climate system.
Okay, so the good times couldn't last forever. The Earth's orbital wobble continued, the summer sunlight in the north gradually weakened, and the monsoon started its inevitable retreat southwards. The Green Sahara began to dry out. How quick was the end? How fast did the human population collapse?
While the drying trend was probably gradual over the longer mid-Holocene period, the final collapse of the human population, as recorded in those SPD curves, was remarkably sharp. We're looking at a massive drop, something like a 55% loss in the population index, occurring over a relatively short period of about 1,100 years, roughly between 6,300 and 5,200 years before present.
A 55% drop in just over a millennium. That's brutal, a huge depopulation event.
Absolutely. A rapid abandonment of vast areas that had been densely populated just centuries before.
And do the geological records, the lakes and the dust cores confirm this rapid shift back to desert?
They do, very clearly. Lake-level records show major drops. Lake Turkana, for instance, had several rapid fluctuations and then a massive regression, a drop of about 90 meters around 6,000 years ago. And crucially, back in our Red Sea core, KL11, the amount of wind-blown dust being deposited, that Aeolian signal, essentially doubled around 5,500 years ago.
Doubled. Wow.
That doubling is a clear marker. It signals the definitive return of hyper-arid, dusty conditions. The desert was back with a vengeance.
Okay, so here's the puzzle. The orbital changes driving the monsoon retreat were slow and gradual, right? Predictable. But you're saying the population collapse was rapid, and the geological markers like dust flux show a sudden shift. Why the mismatch? Why wasn't the end as slow and gradual as the astronomical forcing?
That's the million-dollar question, isn't it? And it gets even more complex because the evidence suggests the end wasn't perfectly simultaneous everywhere. The termination seems to have been locally abrupt, meaning it happened quickly in specific places, but it was also time transgressive. It didn't hit the whole Sahara at the exact same moment.
What do you mean by time transgressive?
Well, the balance of evidence suggests that the drying started earlier in the eastern Sahara, maybe around 7,000 years ago, compared to the west, where the final desiccation seems closer to 5,500 years ago. And similarly, it seems to have started earlier in the north, maybe around 28 degrees latitude, then further south, closer to the core monsoon region around 2 degrees south.
Okay, so if it wasn't just the sun slowly dimming everywhere at once, that points to other factors, right? Maybe those land surface feedbacks we talked about earlier, the vegetation.
Exactly. That regional variation, that time-transgressive nature, strongly suggests that simple orbital forcing isn't the whole story. It points towards nonlinear responses within the climate system, and crucially, the role of land surface feedbacks. Remember how vegetation helped amplify the wet period? Well, the loss of vegetation could potentially amplify the dry period, pushing the system towards collapse faster than expected.
Which leads us directly to the really provocative idea, the anthropogenic hypothesis, the possibility that humans themselves helped accelerate the desertification.
Precisely. This idea, championed by researchers like David Wright, really focuses on that mismatch in speed. The collapse seems too fast, too abrupt, to be explained solely by the slow orbital changes. So the hypothesis suggests that the high population densities, particularly of those newly dominant pastoralists with their large herds of cattle and goats, might have provided the critical push that tipped the weakening system over the edge.
How could grazing animals accelerate the desert's return? What are the proposed mechanisms?
There are several interconnected ways this could have worked, especially in a climate that was already becoming more fragile. First, and most obviously, overgrazing. Large numbers of cattle and goats consuming grasses and shrubs, especially in sensitive semi-arid areas, would degrade the vegetation cover. This exposes the soil to erosion by wind and water.
Okay, less vegetation cover. What else?
Second, remember how plants release moisture. That process, evapotranspiration, adds water vapor to the local atmosphere, which can help form clouds and contribute to rainfall recycling. So by removing vast amounts of vegetation, you are essentially reducing this local atmospheric moisture source. You're making it harder for rain clouds to form, especially as the main monsoon is weakening.
Right. And the third one connects back to albedo.
Yes, this is potentially the most powerful feedback. Removing dark vegetation and replacing it with bare, bright soil or sand dramatically increases surface albedo. More sunlight gets reflected away, which cools the surface. Surface cooling suppresses convection, that rising air motion we talked about. And less convection means the atmosphere is less effective at pulling in moisture from the oceans. It essentially weakens the monsoon pump further.
So the very act of intensive grazing needed to support the large pastoralist populations, created conditions bare ground, higher albedo, less local moisture that actively worked against the already weakening monsoon, accelerating the shift to aridity.
That's the core of the hypothesis.
Right.
And you can potentially add a fourth factor, the use of fire. Pastoralists and even earlier groups likely used fire as a tool to manage landscapes, clear brush, or encourage new grass growth. This too would contribute to removing biomass and altering the surface properties. The synergy of these effects, grazing pressure, moisture reduction, albedo changes, maybe fire could explain the rapid, abrupt nature of the final desertification.
But as other researchers like Jessica Tierney have pointed out, this runs into that classic chicken and egg scenario, doesn't it?
It absolutely does. It's the major challenge in testing this hypothesis. Did the adoption of intensive pastoralism cause the rapid collapse? Or was the climate already deteriorating so badly that people were forced into pastoralism as a more mobile survival strategy in marginal lands, and the collapse happened anyway, merely coinciding with the rise of herding?
Correlation versus causation.
Exactly. Right now, the timing is highly suggestive. The big boom in pastoralism occurs just before the final rapid population decline and desertification. But proving that one caused the other is incredibly difficult with the current resolution of data. We'd need really fine-grained studies directly comparing detailed vegetation records like pollen from lake cores with highly localized archaeological evidence of human and livestock density moment by moment through that transition. That's tough to get.
So we can't definitively say humans killed the Green Sahara.
No, not definitively. But the evidence strongly suggests that human activities, particularly this large-scale shift to pastoralism, likely interacted with the natural climate trend. Humans may have acted as a crucial keystone species in this context. Their actions, concentrated in a vulnerable environment at a critical time, seem to have significantly amplified the speed and perhaps the severity of the transition, pushing the ecosystem across a tipping point much faster than orbital changes alone would have done. It implies that even thousands of years ago, human land use, driven by cultural choices and population pressure, could have profound large-scale impacts on regional climate and environment. #tag outro.
Wow. Okay, so this deep dive has completely reshaped my picture of the Sahara. Let's just quickly recap the main takeaways for everyone listening. First, the Sahara isn't static. It cycles between green and arid states, and this cycle is ancient, driven primarily by predictable changes in Earth's orbit affecting the African monsoon.
Right. And we saw how incredible archives, like the Red Sea sediment core KL11, let us track these cycles over hundreds of thousands of years. We can literally see the signature of massive ancient river systems like the Baraka turning on and off, showing just how wet it used to be.
Then, during the most recent Green Sahara, the Holocene period, the environment wasn't just passively receiving rain. Megalakes formed, and crucially, widespread vegetation created positive feedbacks, amplifying the wet conditions.
And this lush environment allowed for an explosive human population boom, though it lagged the initial climate shift by about 1,000 years, waiting for the ecosystem to mature. People adapted first as specialized hunter-fisher-gatherers, the Aqualithic.
But then came the critical shift, the widespread adoption of pastoralism around 7,000 years ago, fueling another population surge, but also introducing a new, powerful way for humans to interact with the landscape.
And that interaction seems key to the end story. The final collapse back to desert conditions was brutally fast, much faster than the orbital forcing alone would suggest. The timing strongly correlates the peak of pastoralism with this rapid desertification.
While we can't prove direct causation definitively, that chicken and egg problem, the evidence points towards human activity, specifically overgrazing and its effects on moisture and albedo, acting as a powerful accelerator, pushing the already weakening system over a tipping point.
Yeah, it really suggests humans were a major ecological force even back then, capable of significantly altering regional environmental trajectories when combined with natural climate shifts.
So this isn't just ancient history, is it? There are lessons here.
Absolutely. I
Yeah.
mean, the ancient Sahara is this stark case study. It shows how human land use in vulnerable arid and semi-arid lands can interact with climate variability, natural or otherwise, to trigger potentially rapid and irreversible environmental change. Those feedbacks, vegetation loss, albedo change, moisture cycling, they're fundamental.
Which brings us to a final thought for you, the listener, to mull over. If ancient pastoralists, simply by grazing their herds in a vast landscape, could apparently accelerate a regional climate collapse driven by slow orbital changes.
What does that imply for managing similar vulnerable dryland regions around the world today,
Yeah.
especially when the background climate isn't just slowly changing due to orbital cycles, but is rapidly warming due to anthropogenic greenhouse gases? The stresses are arguably much higher now, but those fundamental ecosystem feedbacks are still in play. How do we navigate that?